So you want to build a printed circuit board, but you've never thought that it was actually in reach. Well, I'm here to tell you it is. This is the second video in my series on how to build your first PCB. If you haven't seen the first video, it should be right up here. So go ahead and click on that, look at that one, and get back to this one when you're done. Although if you're just interested in kind of watching along, this video should be reasonably self-contained as well. We just won't go over this schematic in any level of detail because we already created this schematic in the first video. So just a quick review. This is a USB to serial converter. What it does is allows you to connect a USB device, so a USB device on your computer, to a serial UART device. The ideal usage for this would be to talk to a microcontroller and also optionally power it, because this breakout also offers 5 volts and 3 volts out and a ground connection. So you could use this to power your DIY projects and to communicate with them. Not only is it an instructive first project, it is a useful first project as well. I'm going to be the first to say I am not an expert. I am doing a video series on how to create your first PCB, and this series will deliver. I am not giving you a video series on how to be an expert PCB designer. If you want to go into a career in PCBs, this is not your route. This is DIY, this is getting the job done, this is learning as we go. So you might be able to criticize every step of the way, and if you want to, just jump into the comments and tell me what I've done wrong. I'm actually really interested in hearing about it, and I think the folks who watch this video would be interested in that as well. This is a USB device, so we've got a USB-C connector here. We've got a UART controller, and this is the, I forgot the name of this guy, this is the, oh yes, the CP2102N. So that's a very common UART controller chip. We've added some blinking lights so that we can see when it's transmitting and receiving. We have a little reset button that allows us to reset this chip and also allows us to tell other devices to reset this chip. The really important thing here is we have a breakout header, and the breakout header exposes 3 volts, 5 volts, and ground, and the reset pin, and then the important things for our serial communication, transmit, receive, CTS, and RTS, which are kind of serial line control flow dealies. I'm not, a serial expert. I just plug pins in, and if it doesn't work, I move them around, and then it works. And then the other issue that we had to deal with was power and electrostatic discharge protection. So we included a component that handles electrostatic discharge for us. That protects our data lines, so if static electricity were to zap them and so forth. Then we have a polyfuse that protects us in case there's some sort of a short, so that you don't damage anything downstream. You don't want to damage the device that you've plugged this board into. Lastly, we have a 3.3 volt LDO. So this is a linear or low dropout regulator. This transforms 5 volts into 3.3 volts, which is the preference of this chip to handle, and it's also the preference for signaling. We want the signaling, the transmission, the transmit, receive, and so forth to happen at 3.3 volts, because we're mostly going to be talking to 3.3 volt tolerant microcontrollers. Unless you're doing some sort of a vintage thing, you might want to consider powering this with 5 volts. So that would be an option if you wanted to modify this. You could optionally actually make it switchable, so it could be 3 volts or 5 volts, but here we just decided to do 3 volts only. That's the schematic. It's a relatively simple circuit. So now what we need to do is we need to draw the physical layout of the PCB. So we need to implement the theory of the circuit, the schematic design, in reality. It consists of actually placing the representations of those components, the footprints of those components. So here in this schematic, what we've been doing is we've been dealing with symbols, and symbols are very highly abstract representations of this chip. So this is a symbol of the chip, and I was actually able to edit it and make it even more abstract because I moved the pins all over the place. So this doesn't actually represent the physical reality of the chip anymore. It represents a convenient reality for just laying out a schematic. The footprints of the chip are the actual footprint that the chip will have on the board, down to sub-millimeter precision. So they are the layout and the copper pads that the component needs on the board that the PCB manufacturer is going to have to expose. That's what we're going to be laying out. So in our PCB layout, we're dealing in the world of footprints, which are kind of like the intersection of the real world component with the board. It's how they mechanically connect to it. Sometimes there are mechanical holes. So you will see that with our USB header. It has a mechanical connection and a ground connection. Sometimes they'll just have pure mechanical holes where just a piece of plastic comes through a hole in the board to provide some mechanical stability. Again, I want to drive home the beauty of using EasyADA Pro here is the fact that they have a massive footprint library for all of the components that we sourced previously. So we picked components that they have that JLCPCB has and can use to manufacture this device. And they also maintain the symbol library, these symbols that we see here on the screen in the schematic, and the footprint library. EasyEDA has taken care of all of that for you. So at this point, when we're done, and remember that we did our design, we did our checked our DRC, we found that we have no rules violations. So that's the first thing you want to do before you go on to do the next step of creating your PCB. I'm going to do design and update and convert schematic to PCB. Woohoo! And this is going to give us menu, and you can see it also auto-saved, which is nice. So it's going through and it's listing all the components here that it's going to place in our PCB, right? Okay, so immediately we see we've got a big mess here, right? Although it's laid out in somewhat the same manner that it was laid out in the schematic. So it's put the parts down in kind of the right locations, but the first thing we want to do is just kind of take a rough pass at orienting things. So again, we can click on things, we can hit the space bar to rotate them. And so let's put the USB-C port like kind of over here. You see these blue lines, these are called rat lines. And a blue line, you really don't want to see any of them when you're done. They should all go away. They tell you that something needs to be connected to something else. All right, so we can kind of put things around where we want it to be. You know I want the USB on one side. I want this little UART controller here. I want to put the LDO relatively close here. ESD components need to be close to the USB. The polyfuse needs to be close to the USB. These two, and you can see these are the capacitors that are supposed to connect up to the CC1 and the CC2, or not the capacitors, these are the resistors that need to connect to the CC1 and CC2. We've got some capacitors for the LDO, got a resistor and a capacitor for the LED display that indicates that power is on. We've got the transmit and receive LEDs, so I don't know, maybe we'll put them up over here somewhere, kind of get them, just tuck them out of the way for now. So there is I think there's a little bit of a resistor divider here. So we'll put that close to the pin where it's supposed to be. C3 and C4 are decoupling caps for the UART controller. We'll try and pack those in. And you can kind of see, like, these are 0402 components. They're big compared to modern SMD integrated circuits, right? I mean, like, this is a lot of logic packed in to this component, right? And two of those relatively small resistors just cover it. So space is at a premium here. And then our header connectors, I don't know, we'll maybe rotate those a little bit so that they're off over here. And I want to put my reset button somewhere over here along with there. It's LED. I'm not sure what this guy is. This is, so R5 is the pull down resistor for the reset button. So we'll kind of leave it up here. It's got to go in line with that reset switch. Really, so what we're doing here is we're just manipulating these footprints. So these are, the red parts are exposed copper on the PCB. And we haven't really talked about the PCB much. Matter of fact, there is no PCB here because we haven't drawn a board. Now I'm going to introduce the layer tool. We've just been kind of moving things around. This is not the final layout, but let's go over to the layer tool. You can turn on and off every single layer in here. If you want to change the layer layout, so to speak, you can go into the Tools Layer Manager, and we can select how many layers we have, and so forth. So we are doing a 2-layer board. That means there are 2 copper layers in this board. There's one on the top and one on the bottom. And there is a material in between. I believe it's some sort of a fiberglass, effectively. You can do a 4-layer board, and actually 4-layer boards are not all that much more expensive than a 2-layer board, and there's a lot of advantages to doing a 4-layer board. For this simple board, we don't need it. So we're going to do a 2-layer board, and we're just going to have signal on both of them. We are going to actually draw our own ground plane, and that's called a copper pour. So we can draw a copper pour on our board, and we're going to draw a ground pour on the back of the board. So we can look at all the various layers here, and there are a lot of them. Some of these get into very technical details of the manufacture of the board. What we're really concerned with, the number one ones that you will deal with in this project, is the top layer, the top silkscreen layer, the bottom layer, and the bottom silkscreen layer. And that's almost it. And you need to click onto it so that you get the little pencil if you're going to draw something on that layer. If you haven't clicked onto that, you're not drawing on that layer. So whatever layer is selected here is what you're drawing on. Doesn't matter if you can see it, doesn't matter if you think you're drawing on it. If the bottom layer is selected with the little pencil icon, that's what you're drawing on. You can turn layers off so you can't see them at all. So I just turned off the top layer, and I could turn off the silkscreen layer. I could turn off, basically everything. I think there's also the multi-layer. So if we turn off multi-layer, it gets rid of everything that kind of goes through the board. So anything that has a pin that drills through all the layers of the board would be on that multi-layer. So we can get rid of that. So we can turn off everything here if you really want to focus on one particular layer. And I wouldn't recommend doing that to start unless maybe you just want to get rid of a silkscreen layer. Sometimes like just turning off that top silkscreen layer can help you kind of see what's going on, because those silk screens can get in the way of things. Here we have the board outline layer. And so we're going to select the board outline layer, and then we're going to draw a rectangle on it. We're just going to say rectangle, boom. There we go. We've got a board outline layer. Now, it said by default, I guess the default is a fill region. We're going to select a board outline, and then we've got the start. I'm just going to do 0, 0, and let's just call this 80 millimeters for now and 25 millimeters high. Now we've positioned our board outline at the origin, so it's at 0, 0. We're going to select everything, so you can just lasso select everything. I don't want to select the board outline, so I can Command or Control click the board outline, and then, oops, this is one thing. When you drag things in here, you need to actually, you have to hit something on it. So like I can't just like drag in the middle of something here. I have to like hover over and hit it in there. Now we're going to drag all these things up into the middle of our board outline. So now we've got a reasonable shot here. Like this is starting to look like a reasonable layout, right? Now we need to move things around a little bit. We can still change our board outline. Like if we want to come in here and edit that board outline, we can do that again. If we click off of the board outline, so we just click the kind of the gridded background here, we can go over to the properties and see the document properties. And I would suggest taking a look at this so you can look at the grid size here. Units, I would suggest you use millimeters. And then we also have some common settings here. I tend not to change these, but it's good to know where they are. There are rules for all of these, so track width, via size, and so forth. And we'll talk about track width and via size in a minute. So let's go back to our layer manager and let's select the top layer, and we can zoom in. So you use the scroll wheel, or I'm on a Mac touchpad, so I do the 2-finger drag that scrolls in and out. You do command drag, 2-finger drag to scroll up and down. You can do shift up, down, and drag to go left and right. It will zoom in to where the pointer is pointing. So if you want to zoom in on something, you can just kind of zoom out and then point at it and zoom back in is a good way of kind of getting there. And then you can use the control scroll wheel or control two-finger drag to position properly. Okay, so first things first is we want to connect up these resistors. So we're going to put these resistors relatively close. You can drag around their little labels, get them out of the way if you want. And now we're going to go to our component toolbar up on top here, and you can see the wire tool here. So if I hover over it, it says single routing. So that's a single wire routing. And when you click on that, you can see the track width. For the track width, 0.254 is just fine. That's 10 mils. And it's just the default, and we're going to take it because it's not terribly important on this board. What I think is important is understanding why you picked a particular track width or trace width and being consistent about them. So don't use a 0.254 track width here and a 0.2 track width there and a 0.3 track width there. Be consistent about it and know why you're doing it. For signals and for USB and so forth, we don't need a particularly wide track. Actually, 0.254 is relatively wide in the scale of things. You can go much smaller than this, but we don't need to. So it just makes sense to stick with the default here. For routing power, we might actually get quite a lot larger. For attaching a decoupling capacitor, we might want a little bit more copper to provide a very low impedance route to that decoupling capacitor, so we'll use a wider trace there. So we're just going to select this. We're going to go click on the pad and drag over to the connection, and Bob's your uncle. It's connected. That's awesome. Now, you can start dragging this thing around, but you notice when you do that, it just becomes disconnected. And it's like, okay, now you can come over here and you can grab the end of this there and draw it over there. So if I moved it, but if I move it back, now it goes away. Now I want to talk through, because this is really, really important. So when it's connected, I can just kind of grab it and start dragging all around. And this is what I mean by interactive routing. So it is, interactively routing around all the obstacles on the board. So it's not going to draw a line through this R1 like I can't drag down through here. So I can drag it around and I can move things around, but it stops me from, it stops me at the border of other components, right? So it is interactively implementing the rules of the board, but it's not doing a particularly great job at routing. And I wouldn't suggest just kind of grabbing a whole track and dragging it around the board like this. It's not a particularly good way of doing routing. What I would, however, suggest, you can click on a track and click on it again. I believe you can even double click. It's roughly the same. So you can double click on a track. And you get one segment of that track. Now this is useful for deleting things, so you can delete things in the middle if they get messy. And then you can also grab it and you can move just that particular component. So notice it's not like drawing crazy lines all over the place like it was previously. It's just doing what it has to do to move this component. So let's look at the difference between that again. If I just grab this and the whole line is highlighted and I start dragging it, we get crazy town, right? This is, all sorts of crazy stuff. This is not what you want. It's doing, really weird stuff on the end here. I don't love that. So let's go and double click. Now if I drag this, all it's doing is making the updates that it needs to update that particular line segment and move it. So that's the way that I would suggest that you use the interactive router, by just selecting one item and moving it. And one other thing that I will note, when you're drawing wires, you don't need to get all the way there. So you can just kind of stop partway. So maybe if this component were up here, so say you're drawing a track and you're like, okay, this is far enough. You just hit the escape key and you're done drawing that track. And then later on you can come along and say, okay, I'm gonna finish that and connect it up. So you can do them in parts. And then another cool thing that you can do is that you can draw over something. So if you thought that this little bend here wasn't right, I can do this and that, and it removes the alternative path. And that's a really cool little hack in terms of like, so for example, like say you didn't like this and you're like, that's just much simpler to go from here up to here. Let's go ahead and draw that, and boom, it just replaces it. So that's, the interactive router is relatively intelligent and useful if you understand how to take advantage of it and don't just like kind of willy-nilly drag your tracks around like this. Don't do this. Matter of fact, my #1 use of the undo key is when I think I've grabbed a line segment in a track and I accidentally grabbed the whole track and I dragged it all over the place, and you know, there's no way of fixing that, right? You just gotta Control Z. So anyway, let's get back to putting this particular component, connecting it up. So we can see the rat line is still there. If I draw a line out here, if I draw a track, the rat line goes away. Here again, draw a track, the rat line goes away. We want to wire this thing up to ground. So it is a pull-down resistor, so it's connected to ground, and so it's got to be connected to ground. So one thing we could do is we could just draw a little wire and hit escape, and then go up here and get the via tool, via, and click that, and you got a ground via. Now, JLCPCB handles via, what's called via in pad, and it can just greatly simplify designs and make things look a little bit better. So I would just recommend that you put that via right in your pad, and we're going to do that right there too. Now, we've got a problem in that this says that it's a ground via. Well, what's a via? A via is a hole through the board that the manufacturer drills, and then they clad it with copper, right? But they have it only connect to the particular layers of the board that you specify it does. It's always going to connect to the, for simple boards like this, you can have things that are called blind vias that start at intermediate layers in a board. That's advanced stuff. I don't do that. It's always going to connect to the top layer of the board, and then it can connect to one or more internal or bottom layers of the board. Here with a 2-layer board, the via can basically only bridge the top layer of the board to the bottom layer of the board. So when we say this is a ground via, and we acknowledge what I just said was true, it's going to connect the top layer of the board, so it's a hole drilled through the board with a copper cladding and a copper skirt at the top and the bottom that are physically, electrically connecting the top of the board to the bottom of the board. There needs to be a ground plane on the bottom of the board, right? And there isn't. So what we're going to do is going to go to the bottom layer and we're going to draw that ground plane. So we're going to zoom way out. So we're going to select the copper area tool, and you just, somewhere inside the board outline, if you go outside the board outline, I think it'll just get cut off. But the copper area should probably not extend up to the board outline. It should stay within a certain margin of it. And I think there's actually some rules around that. So you'll violate a design rule if you put it too close to the board edge. So I click and drag and then click again in the end, and we get a pop-up that says, okay, this is going to be a copper region, and we're going to name it Pour 1. I guess I'll call it ground pour. It's on the bottom layer. I could put it on the top layer, but we're going to put it on the bottom layer. It's going to be ground. And you can see all the nets here, so you can see those kind of auto-generated nets that are out there, and then all the other ones as well. So one thing you need to keep note of is that there's an algorithm that detects all of the through holes, so basically all the holes that are drilled through the board, and whether or not they need to be connected to the ground plane. A via that's labeled as a ground via will be connected. So if we go over here and we look at this guy, there's no circle around him on the ground plane. But over here, we have some through-hole pins that connect to the 3.3 volts. And obviously that can't connect to the ground plane. So there's an exclusion area around it. So there's a hole in this pour. And the algorithm that flood fills it knows how to do this. But it's a relatively compute-intensive algorithm, and it doesn't run all the time. If you want to refresh it, so one thing that you can get into trouble with is, say, you move one of these components, right? Now, suddenly If you do design rules checking on this, you're going to violate everything, because now these components are physically connected to the ground plane, every single one of these pins, because they lost their exclusion hole. One thing that you can do is you can come into the properties for the copper area and do rebuild copper area, and that fixes it. So it filled in those old holes that it no longer needs, and it drew them around it. Another thing that I would recommend that's even easier is to just learn Shift B. Just kind of almost reflexively hit Shift B, and it will rebuild every single copper area in the project. So lots of times when you thought your board was relatively clean, you made a minor change and you go to check your design rules and there's like dozens of violations. Usually that's because you have not redrawn your copper pores on the board. Okay, great. So we've got R1 and R2 wired up. The next thing that we want to do is we want to wire up the VBUS. So VBUS has two connections, and we need to connect both of them because people can flip the cable over, right? You can reorient a USB-C cable. For this one, we're actually going to draw a relatively beefy 0.4 millimeter track. And we have a reason for that, because a 0.5 millimeter track won't fit through there's this little hole here. You can see I'm highlighting it. A 0.5 millimeter track won't fit through there. Now, the next thing that we're going to do is, so you can see the interactive router working, and you don't want to like let the interactive router just keep doing its work as you drag. So what you can do is you can kind of constrain it. You can click as you go. So if I like where a particular vertex is, say right there, I think that's a good position, I just click. And now no matter what I do, that is anchored. So I'm going to keep going and then come down here. I'm going to click there and there. Okay, so I've wired those two pins to each other, and maybe, I don't know, maybe I don't like that. Maybe I can click that and drag it a little bit there. That's better. Okay, then I need to take VBUS over to this polyfuse, and we're going to bring that in relatively close here. Do 0. Here, I believe we can get away with 0.5. For good reasons, for boards that are way more complicated than this, the interactive router will try and guide you to a lot of 45-degree angles as opposed to a 90-degree angle. You can get it to do a 90-degree angle, you can force it to do it, but it will prefer 45-degree angles. So I'm gonna do this. Oh, no, there. Okay, and then boom. Okay, and the next thing I want to do is I want to wire up the power. You can pull quite a lot of current through this little regulator, and we expose a 3.3 volt pin out of this particular board. I don't want somebody to put a high consumption device attached to this board and burn up the little regulator on your board. And that's actually relatively easy to do. If you remember in the last video, I said there might be people screaming at the screen to say, don't use this regulator. Don't use it. It's very inefficient. It gets hot and so forth and so on. Well, yes, it will. And there's ways of dealing with that. So we're going to put a large copper pore around it to help it conduct the heat away from it. So we're going to go ahead and associate our capacitors with our particular pins here. So we've got the decoupling capacitors that want to connect to the 3 volt, and then we have the decoupling capacitor that wants to connect to the 5 volt. Let's get that little label out of there. You do not want to draw silkscreen. So the yellow stuff here is silkscreened, so it will be just basically printed on the board. I'm not sure if it's silkscreened anymore. It's probably like squirted on the screen with like dot matrix inkjets or something like that nowadays. But you don't want to draw that over pads. And as a matter of fact, I think there'll be a design rules check to make sure that you haven't done that. So you just don't want things like that. You want to move those labels out of the way, and you don't want something like this either. You don't want, even though, say, maybe the pads are not overlapping, that silkscreen is meant to kind of represent a little bit of a visual buffer. I've had cases where I do put things that close and I just get rid of the silk screen. That's perfectly legitimate as long as the copper pads are not too close either. But for our cases here, we can just keep that little silk screen around it and just make sure that we don't get things too close. So we're going to talk a little bit about decoupling capacitors. You want those decoupling capacitors as close as possible to the pin that they're filtering for, and you want a nice wide track to them. So here we're going to do, let's just go ahead and select that track, and I don't know, there's no good reason not to do a 0.5 millimeter track there. And we'll do another one down here and make that 0.5 as well. Yeah, it just doesn't matter. So let's line that up a little bit. And you can see there's, I don't know, sometimes it draws like a mess in here. So we can go ahead and delete that and there. And then we need to put the ground vias. So ground and ground. So we've decoupled this low dropout regulator. It produces 3.3 volts on each one of these. We have to ground that. Now we're going to, for thermal reasons, we're going to put 3 vias here. And this is the first time we're going to talk about the thermal nature of a via. So a via is clad in copper. Copper conducts electricity. It also does a very, very good job of conducting heat. What we can do is, if this component generates heat, the heat will flow through the vias, the ground vias here, from this grounding pad of the low dropout regulator into the giant heatsink of the copper backplane in the back. Now, 3 vias aren't going to sink a lot of heat, but I'll take it. So I'm going to put, a couple extra vias in here, that more than you would need for the current flow, way more than you would need for the current flow, certainly more than you would need just to make that electrical connection. And then the next thing we need to do is to connect our 5 volts. So VBUS goes through the polyfuse and becomes what's called the 5 volt net. And we connect that around here. And we're going to use another 0.5 millimeter trace. Maybe drag that down a little bit here. There we go. We know that we've got 0.5 millimeter traces. We got 0.254 millimeter traces, which are kind of the default, the 10 mil traces. And we've got a 0.4 millimeter trace that we use because the 0.5 was just a little too big for the constraints. So we got 3 different track widths in this project, and that's probably all we'll need. So let's try and stay consistent and use those track widths. Now that we've got power, we can hook up the chip, right? So let's find our chip, and it's probably not in the right orientation. It is not. We need D plus in and D minus in to be facing the USB port. So if I drag this over here and line it up kind of in the middle, so the D plus and the D minus are in the middle of this, but we want them to go kind of lined up like that. So that's a good position for our chip. It's okay to have silkscreen, overline silkscreen. So we can put C3 over here. And these labels, we'll just move them around. We'll figure it out eventually in the end. I think we can just kind of get these out of the way. I don't know that we need those up there in the way of that chip. So now we're going to wire 3 volts over. Great. So we can see that it gets 3 volts here, and these 2 pads here actually both have 3 volts. So one is VREG in and one is VDD. And those are both going to be set to 3.3 volts. So we can treat them almost physically identically, and we'll actually think we're just going to wire them together out here. This should be okay, like that. And then we need to decouple the 3 volt like this. So we just draw a line through here. And here we've been doing 2.54 millimeter. We can fatten this one up a little bit. Let's see if we can get away with 0.4. I think they made that pin a little bit wider so that you can do that without getting design rules errors. So that allows you to have a little bit lower impedance connection to the decoupling capacitor. So we've drawn a trace from one to the next capacitor and then from the next capacitor to the next. And now we need to wire up our grounds. And we'll deal with the labels in a minute. Now here we have one of our first conflicts, is that we need to get 5 volts from here through this resistor divider network and up to this pin. And we can't really do that very easily. We could route it up around here, but we're going to have to route our USB stuff through here eventually. We're going to use our first use of a via to route around these sorts of issues. So what I need is I need a line that can basically jump over this 3-volt line. And really what it's going to do is it's going to jump under it. So I'm going to draw a track here out a little bit. And when I'm done, I'm going to hit escape and I'm going to put a via in the end of it. And when I do that, it'll ask, do I want to use ground or that kind of net identifier that it automatically generated. Obviously, I don't want to tie this signal to ground. I want to route it elsewhere. So I'm going to say, okay. And now I'm going to replace a via on the other side. Well, actually, I can place the via in the pad here if we want to get a little bit tricky. So I'm going to place that via in this pad, which is exactly where it needs to go. You notice the net name was the same there. And now what I can do is I can go on the bottom layer. So now we're drawing on the bottom layer, and I can draw a trace between these 2 vias on the bottom layer. Although they're not quite lined up, and there we go. So it's got to zig and zag a little bit. We can clean that up eventually. And now remember to come back up to the top layer. So now we've avoided this collision, although you'll see there's a little yellow X there. That means that this via is too close to that track. So one thing we can do is we can kind of grab the track and move it away a little bit. And there, it seems like that's okay. And now we've got to wire up our divider, our voltage divider. And here we put a via to ground, so it's going to connect to the ground plane. And then we just want to do some normal size tracks between here, and then here to 5 volts. The 5 volts goes through the voltage divider, steps it down to a lower voltage that then gets detected by the pin on the chip that tells it that 5 volts is on. The next big thing that we have to deal with is something called differential routing. On this particular situation, we're routing 12 megabits per second USB. Differential routing really doesn't matter much at all. But I talked about this in the last video. If you're doing, say, high-speed data signaling that uses differential signaling, it will matter. So for Ethernet ports or for a differential video signal like DVI or something like that, differential routing does matter quite a lot. We're going to use a little bit of a shortcut here. Ideally, what you need to do is you need to use a differential signals calculator for your particular board stack up. And we can go ahead and do that. So this is a controlled impedance calculator, and it's complicated. We're going to tell it that we have a 2-layer board. So USB impedance requires 90 ohms. So we're going to put 90 ohms in here, and we're going to select coplanar differential pair. So that means there are 2 lines, so the D plus and the D minus are going in a single plane, differential pair, and they are on a signal layer L1. So the bottom ref is the reference ground plane. Differential pairs like to run close to each other so that their magnetic fields kind of cancel each other out. And then they also need a reference plane to control electromagnetic interference and to provide a ground return for that differential pair. And depending on the stack up of your board, in other words, how the layers are, how many layers there are in there, how thick each one of the layers are, the thickness of the material in between the layers, and then the dielectric properties of those layers kind of determines by a whole lot of physics how wide your traces need to be, how far apart they need to be, and so forth. So we're going to go ahead and calculate this, and we're going to put our in millimeters and do calculate. So it says our trace width needs to be 0.43 millimeters, which is absolutely ludicrous. And this is where we're just going to fall back on something simple that works. And the trace spacing needs to be 0.2 millimeters. So they need to be 0.2 millimeters apart. And that's not that big of a deal, but the trace width of 0.4 millimeters is really almost comically big, and we don't want to draw that. That's going to make things very difficult. But it doesn't matter for 12 megabits per second, just standard high-speed USB. It really doesn't matter. So we're going to use a shortcut, which is just a trace width of 0.2 and a trace spacing of 0.2. So we're going to ignore what the calculator told us. Now, this is one of the reasons why you might want to use a 4-layer board. So with a 4-layer board, if you come up here and redo your calculations, you get a trace width of 0.14 and a trace spacing of 0.2. So your traces are much, much smaller because those ground planes are closer to the, you don't have that big thickness of the board. You have those inner planes that are a lot closer. We can go into the design menu and click on our design rules and then go into differential pair. And we want the stroke width to be 0.2, and we set them all to 0.2, and the differential pair min spacing to be 0.2. And then there is something called length tolerance. You would like those differential pairs to be almost identical length, right? Because you're relying on them following basically the signals following the same path and the same length path so that their magnetic fields kind of cancel each other out. If one wire runs a little bit longer, it doesn't have a companion to cancel it out. I have a relatively high tolerance here. I think this is in millimeters. Again, because we've got a very short distance here and we've got some reasons why things aren't going to work well for us. So we have a relatively high tolerance just to get the design rules to work. But again, because it's USB, relatively low speed USB, this doesn't matter all that much. So we set up our design rules for differential pairs. Now we want to draw our differential pairs. And we go to Route, Differential Pair Routing, and we're going to click on one of these differential pairs. And it says we have no differential pairs defined. Do you want to create a differential pair? And I'm going to say, yes, I do. And we have D1 in as one of them, and I'm going to click to select the other one. So we'll do D. Can I click it? Okay, D. There we go. Oh, I got both of them. Crap. So let's do D plus. Okay. There. So we got D plus in and D minus in are selected. So we're going to go ahead and confirm that. And now we should be able to route, differential pair routing, click on here, and look at that. It is beautifully drawing the right track lengths, and it is keeping them together as we go. So keeping them spaced out properly as we go, as much as it can. So now we're going to run into a problem. So we've got to hit these two pads here, oh boy, we're gonna have a little bit of a problem. So we're going to come around here, we're going to click. There we go. So it kind of did its best, but this trace is obviously much longer than that one. Them's the breaks, right? And now we need to route out of this from here, and that's actually a different net. So we're going to go ahead and confirm that we want to do a new differential pair. We'll call it DP2. We got D plus selected, and we're going to select D minus as well. Okay, so confirm, and now we're going to do route, differential pair routing, boom. And now we need to go to the chip. Okay, that's not too bad. We can clean that up, and then I think we need to move this up a little bit. drag that out a little bit more. So we can just manually draw these as well. So I need to connect this one to that one, and this one to that one. And those are not great. So we can come in here and we can just kind of select that. There we go. Make it a little bit cleaner. Select that one. And everything that we do, you know, we get this little differential pair length tolerance. So you can see 1.372 millimeters. So we're within that relatively tolerant rule that I created. So I think we're reasonably good there. This is the way you should do it. It will make your USB more likely to work. It's probably pretty likely to work regardless. And we didn't exactly follow the JLCPCB impedance calculator rules either. We just took a shortcut. We used half the track width. Now we're going to wire in ground to this chip. And then we also have to put in VBUS. And we've got, I think, just enough room to sneak VBUS in here, especially if we move this out of the way a little bit. So now we got VBUS. And the cool thing about this particular tool is that when you hover over a net, it will highlight everything that's a member of that net. So you can see everything, the wire, the track or trace, the pads, everything is highlighted. So you can see, okay, I've got to draw a line from VBUS. Boop. 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 There, now we're connected. And that one doesn't need to be a particularly wide trace. We're just going to do a 0.254 millimeter trace. Next thing, let's do the LEDs. So, and one thing is if you want to select things, you can hide a layer. So right now I had the problem I was trying to like lasso select these LEDs, and I just selected and dragged the background pour, which is crappy. So what I want to do instead is just hide the bottom layer, and now I can lasso these and kind of move them around together. So I can do. And one feature I wanted to talk about here really quick is that you can, if you're worried about kind of aligning things manually, like if you don't feel like you have a very good eye, like is that perfectly aligned? You can select one, select the other, right click and do alignment, and then say align left, align right, align top, align bottom. So I'm going to align the left, and look, they snap together right then. So I would definitely recommend checking out this alignment and distribute methods. There's a ton of things here. So if you got, typically if you've got like a lot of components that you want to arrange in a grid, or you want things to look symmetrical and beautiful, you can use the alignment and distribute menus to handle that. There we go. And then these sides both need to go to 3 volts. And unfortunately, I'm going to have a lot of stuff going through here. So I'm going to have a lot of signal traces going from this chip all the way down to the end of the board. So I'm not going to be able to get 3 volts just like straight through here. It's not going to work. And, you know, I guess I could like go all the way around, so I could go all the way around here and come back with my 3 volts to power these. But I think it's a little bit easier just to go this way. So we're going to do a line from here. And you can see it's highlighting where I need to go even. So it's showing me those capacitors there. And it's showing me, you know, that I need to connect up to there. So it's very, you know, it's a good tool in terms of like highlighting what you need to do as you're going about it. Down to there. Great. So we've done that. And note as well, like I drew this trace right underneath the USB connector. Remember again that we're drawing in a 2D plane, and these components on top of the 2D plane only intersect with it in terms of the holes that they have. So this USB has a post hole that's grounded, and I think it also has a mechanical hole here as well. So those are the only places where it intersects with this plane. Everything else underneath of it is fair game. We drew traces right underneath of this chip as well. So it's fair game to draw traces underneath the chip, and you can even draw traces through in between these pads sometimes if they're widely enough spaced. And this chip is probably not widely enough spaced to be able to do that. But I could draw a trace right through this resistor, because there is physically nothing there. The resistor connects to only its pads. There's nothing in the middle of it. And so you can sneak wires, you can sneak traces and tracks anywhere through a gap in a footprint. So now I'm going to draw that, and that makes the lights blinking, right? So you can put, now we've got room to put this here, put that there. And the next thing we can do is we can actually draw some text. So we're going to do TX and height 1.8 millimeters. And boom. Okay, so that's a good size, but it's red. That's a little weird. Why is it red? Because all the other silkscreen is yellow, right? Well, we drew this on the copper layer. And so what it's going to do is expose copper. Well, I'm not sure if it'll expose copper, but it will leave copper there. It won't etch it away and probably cover it with solder mask. So you might actually see this on your board, but it's not what you're expecting. So that's because it's on the top layer. I want it to be on the top silkscreen layer. And when I do that, you see it turns yellow. And then I'm going to copy and paste that and put it here. And we're going to call this RX. And you know what? I did that backwards again. Okay, nice. Great. So we have our transmit and receive here. And don't feel bad on putting silkscreen over tracks. And when I say track or trace are interchangeable. They mean the same thing. It's basically the wires on the PCB. Don't feel afraid to put silkscreen over the top of them. You just don't want it over a pad on a chip. We need to route this resistor. So this resistor, its route line says, where is it? So it's connected to 3 volts and it's connected to RST. Okay, so that's cool. We can just put it right there, right? Because it's got 3 volts right there, right? Yeah, and then we can bring our RST through here. And here I'm just going to do what I said before. I don't exactly know where that's going to go, so I'm just going to hit escape and let that wire die because I don't know, what adventures that pin is going to have. And you can see here, any of the pins that are just numbered and don't have a label, those are the not connect pins that we had. We still have the transmit and receive, the RTS and the CTS pins to hit out there. While we're in here, we can go ahead and ground this UART controller chip. And what we're going to do, the way we're going to do that is we're going to do a ground pour on the top layer. So we're going to hit basically the entire footprint of this chip, and like that. And we're going to say copper region, we're going to say top ground. And top layer, ground, boom. Okay. And then we'll do Shift B. It's not terribly exciting. It's got a lot of rules that say all these other things don't want to connect to ground. So it's trying to avoid drawing the ground fill there. So now we need to put a couple of ground vias that actually connect this top ground to the bottom ground, right? Let's see if Shift B, I don't think that did anything new. The UART controller chip had this nice big ground pad in the middle. We've got a ground fill that automatically connects the other ground pins to it. So this chip is well connected to the ground plane. So let's go ahead and bring out our signal lines for transmit. And we're gonna try and go up a little bit because I know that I want a big copper area for that LDO. And so I want to go around it. Okay, so we RTS, CTS, And you just kind of have to get a feel for how the interactive router works and play around with things. Remember that Control-Z is your friend. And if you want to get out of designing a wire, hit escape and it will just stop at the last area where you drew something. And I think we've drawn all the traces out for the stuff that we need to connect. So they're going to need to connect down to here. And we can go ahead and we can kind of clean these up a little bit and maybe select this one first. And this one and this one. No. This one first. And Control select this one and do alignment. Vertical align centers. Now, please select the reference object. Okay, so it wants me to say this one is it. Great, so that did exactly what I wanted. So these things are now perfectly aligned with the center a little bit. Great, we'll worry about that in a bit. So we got to draw the wires that connect that. We've got to draw the wires that connect the 3 volt, the 5 volt, and the reset to here, and we're basically almost done. We've still got this LED for the 3 volt as well. But now what we've got to do is we've got to deal with the heating issues with this LDO. So we need to have a big copper pour here. We're going to draw a rectangular copper pour, maybe as large as we can do here. Let's go for like 25 by 20 roughly. There we go. So, and I think we can recenter this stuff a little bit in the future. Well, let's just get this stuff up a little bit higher. So we take a look at the properties of our copper pour. Oh, it says it's a board outline. No, it is a copper region. It's on the top layer, and then we want to put it on the 3.3 volts net. And so we're going to get all sorts of issues here. The LED doesn't need to belong in here. But then we see a cool thing here. When we zoom in, this resistor actually needs to be on 3.3 volts. So we can just park it right there. It's happy. So now we've got a little bit of a problem in that we need to get 5 volts from here. So if I hover over this, you can see it's highlighting our output pin. We need to get 5 volts from here to there, but we've got a 3 volt trace that's crossing. And what I'm going to do is I'm going to just delete a portion of this 3 volt trace because I see another way I can go with that. And we won't worry about that right yet. We are just going to draw our 5 volt trace from here down to here. Great. And let's make that thicker because we want it to be 0.5 millimeters. Great. And do Shift B. There. And it actually kind of cut off the corner of our copper pour here. The other thing that we want to do is we want to draw this copper on the back side as well. So this will help to spread heat a little bit. Copper on the back side will help to spread heat even more. So we're going to go to the back layer. Actually, I think I can just copy this. So let's do Control-C. Select a reference area. Go to our bottom layer. Control-V. E. I can barely see that. I can kind of see that outline. But it's still saying it's the top layer. We have to put it on the bottom layer. And then do Shift-B. Okay, now we can see that on the bottom layer we've got our ground plane, and now we've got this cutout for our 5 volt layer as well. And then remember when I talked about how the copper plating in a via conducts heat, we need to put in thermal stitching vias between these two. So if I go back up to the top layer and I click on here, I can say place or remove suture vias. So we're going to add them. Great, it gave us some suture vias. And then we want to add some in the pads as well. So here, this pad is designed to be thermally conductive. So we can add some suture vias. It's going to be physically bonded to the top copper, but then we can also put some thermal vias through. Great. And then we can put some here in this pad as well. So now we've got 2 planes of copper to dissipate the heat from this chip. Okay, let's go ahead and wire up our 3v3 LED and the rest of our headers. 3 volts we can wire directly from here. Sneak those guys up a little bit more. Draw our reset. Ah, come on. Okay, there we go. Make him straight. Okay, and ground the reset button. So this basically just pulls that reset button to ground because it's normally pulled up to 3.3 volts, right? So this keeps the chip running. You push the button, it pulls it to ground, it resets it momentarily. So it's a momentary reset. I've got to route these around here, and we're just going to try, I think this will work if I kind of go around this way. Am I going to line up right? Yeah, I am. So luckily CTS can sneak in here. And you might need to try this several times. Like if you did things wrong and it looks arbitrarily complicated, just delete it all, come back and try it again. Try it in the reverse order and so forth. And then we've got to route our RSTB from there to there. And I think if you look, oh yeah, we've got one issue yet, right? So we had to delete this 3 volt guy. And why aren't there any, oh, there is a rat line, right? So it's saying this 3 volt to here. So you can see the rat lines, the presence of a rat line is telling you that you still got some unsatisfied connection here. So the cool thing is remember I said you can route through components. The polyfuse has this giant thing that goes through the middle of it, and I've got 3 volts right here and I need 3 volts down there, so I should just be able to draw a line straight through the middle of that darn polyfuse, right? And that satisfied my rat line. So now if I zoom in here, I don't have, well, no, I do have a rat line here. Ground, oh, I see, I didn't ground my LED. Ooh, zoomed way in. Okay, so there was one rat line that was left. You know what, that one little via underneath the chip is bugging me. I don't think you need it. It was just bugging me. So one thing that you might notice is that these traces aren't aesthetic, and they are absolutely fine. You could send this board off and it would work just fine. Well, assuming there aren't any other issues in it. What I want to do is I want to clean it up a little bit. So what that means is coming up with some symmetry and reason for things. So you don't want to push traces too close, arbitrarily close to one another. I have a relatively small space up here and they're relatively close to each other, but they're not very close. Like you, in terms of like the limits of how close you can put them, that's very close together. Don't do that if you don't need to, and you don't need to here. So you want to spread them apart, but you want to spread them apart equally. So you want to have kind of equal spacing between them. And we can see that we do have relatively equal spacing. But then when we get over here, we get into a little bit of a mess, and we can correct that by just selecting the segment and bringing them down, and then bringing this one up until the spacing is similar. Does that look good? Yeah. And when it does look right, you'll notice like the vertices kind of follow a line. And then this one's a little goofy, but maybe he's okay to be goofy. You know, he's fine there, right? So that cleaned that up quite a lot. And then if we're out here, well, these things like loop way out, they don't really need to go that far out. We'll probably want to get that space back, right? We don't want our board to be that giant. So we can kind of pull those in. But then again, remember we want to keep that spacing somewhat similar. And then deal with these corners up here. So, I don't know. No. Again, you want to be very careful to only select the line segment. Does that look better? I don't know. That looks reasonable. Doesn't look as messy as it did before. So are we ready to send this off to order? Well, not really. I am absolutely certain we've made some mistakes here. So let's go ahead and save this and go into our design menu and check our DRC. Sure enough, we've got some errors. Not a ton of errors. On such a small chip, I'd be surprised if we had a lot of errors, but let's check them out. So it says that object 1 is disconnected from other objects of the same network, TH pad, so that's a through-hole pad ground. So he's saying that this ground pin is not actually connected to grounds. Let's do Shift B. Oh yeah, we just needed to reflow the that ground plane layer. So I did Shift B, and that repours basically all the layers and hopefully connects them up to the things that they're supposed to be connected to. So now we can do design, check DRC, and it's still saying that is an issue. Oh, sometimes it can be a little misleading, I think. So we forgot to do the through-hole connection, or we forgot to do the ground pins here and here. So let's see if that fixes that. Design, check DRC. Okay, that's much, much better. He's still complaining about this one. I'm not sure what's going on here. I think it might be like a proximity thing. Sometimes it's a little confused. And this, oh, you know what? This is a legit issue. So these grounds are vias, they go right through the board, but remember we put a 3.3 volt plane underneath this chip, right? So the ground layer is not here. What we can do is we can pour a little ground stub that bridges from this ground pour, the big ground pour that's the entire chip here, into here. So let's go ahead and try that. A copper region ground pour on the bottom layer. Okay, let's see, and then see if that, Shift B. We need to go into the Tools, Copper Manager, and we need to give this extra little ground pour priority. So I think it was this pour 4, so he should be highest priority. Apply, Shift B. There we go. Great. So that's a cool little trick. If you go into Tools, Copper Manager, you can see previously that 3.3 volt copper pour had all the priority, so it got drawn first and everything else had to go around it. So now I made the pour 4, that little tiny stub that I made that comes out here, I made it the priority, so it gets drawn and it will physically connect this. So it's a tiny little cutout here of that 3.3 volt ground plane, but it's not going to really disturb it. It's still going to have all the thermal capacity it needs to disperse that heat. Design, check DRC again, and we're gold. A little bit more text here, so let's do Control C and do V, 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 and then 5. I think that looks pretty good. Go ahead and select these, paste, and RxD, TXD. So I think that looks pretty good. And I think we'd like to put like a little summary of what this is. So let's do a text and call it USB breakout board. And if you want, you can put graphics on here if you want to put like a cool little design. I'm not going to do that. Save some time. But you can import graphics. You can put stuff on both sides. So silkscreening is nice in that you can put it on both sides for free. I think I think we're good. I think we're ready to order this puppy. But one thing we can do is double check our 3D view before we send it off. Take a look at it, make sure that none of the real world 3D parts actually collide. There's no, no conflicts. Everything looks spaced well. Sometimes you might have drawn text in the copper layer instead of the silkscreen layer, and it become really evident here that things aren't looking quite right. So yes, we have nice big silkscreen. All of our pins are right. All of our identifiers are rotated properly. It's a very clear, easy to read board, very simple board as well. And then we can see our copper area on the back, so that's the 3 volts, and this is the ground plane and our little cutout for our ground tab on our low LDO regulator. And this is fun. When your menu is too small, the menu is truncated, so you won't see the order option here. So you have to hover over the edge here and do order. And I got tripped up by this for like 15 minutes once. I couldn't find how to order my PCB. So we're going to go ahead and order our PCB. So we're going to do order PCB. And it says, do you want to check the DRC first? Yes, always do that. But we already did that before. But this is a good double check because JLCPCB wants to make sure that you're not ordering crap that's not going to work, right? And it says that the Gerber, the pick and place file, and the bill of materials were all generated. And we're going to click OK. And it's going to automatically upload them to JLCPCB. And I need to go ahead and log in. You can see our files are being uploaded. Great. And we've got a little Gerber viewer up here, and we can click that out and take a look at it so we can see their interpretation of it, which is relatively close to what we saw in EasyEDA. So now what we're going to do is we're going to basically ignore everything in this list. By default, everything's set perfectly. There's a lot of stuff here, and you could have fun setting different things and so forth. You don't want to touch a darn thing. Don't be afraid to poke around, but put things back. You can see it's already identified that it's a 2-layer board. It's got the dimensions of it. And the number of PCBs that we're going to order. If you have any remarks, like if you had a particularly complicated PCB or there was something unclear, you could put some remarks in there. So we're going to do PCB assembly, and what we want is we want economic assembly. We don't want standard assembly. And here we can select either 2 or 5. 2 is really not going to save you much money in the end. So I would just recommend getting 5 unless you really don't want them all. Like, give them away, sell them, take them apart. Yeah, I don't know. Maybe you could desolder the USB connector and use it for something else. Who knows? But it's not going to save, like, it will save you, like, I don't know, $5 or $10 to do 2 instead of 5. And we can see over here the charges and so forth, and it's saying, well, $4. Well, it hasn't calculated any of the assembly or parts costs yet, right? So we go ahead and we do next. And here we see our PCB, and we can look at the back, top, and the bottom. Everything looks good. Go ahead and do next, and it's going to go through our bill of materials, and it's going to double check to make sure that JLCPCB actually has the parts that you need. And because we did a really good job, we picked a lot of basic parts, you can double check and make sure that all the extended parts you had, you didn't have an option. So yeah, sure enough. And the basic parts, and you can see all the prices, so forth. So relatively cheap parts here. The one expensive one is the UART, but we're getting 5 of them, right? So I think it's less than $2 a piece. So that's the biggest ticket item on here, is that UART controller that we bought. But we're getting 5 of them. So you could save, again, a little bit of money by just doing 2 of them. But you can see all the rest of this stuff, you're not going to save a ton of money, right? The parts aren't a huge amount of this. If there were any errors, so sometimes it might be ambiguous. There might be more than one part that hits I've had weird situations where whatever search algorithm it's using to match up this list, even though it has the JLCPCB part number on here, sometimes it'll find 2 or 3 parts in the library when it goes to match them together, and I'm not sure why, and you have to pick the one that wins. Sometimes it won't find a part, so you could have had an error, or maybe they don't have that part anymore. So in that case, you would have to find another part or make arrangements to maybe hand solder that part if you have those parts in-house, or order them elsewhere, something. So we do next, and now we're going to walk through the component placement. Now, because we used Easy EDA, whenever you use Easy EDA, it nails this. Like, it just, there's never any problems with component placement and component rotation. It always nails it perfectly. If you're using KiCad with Easy EDA, sometimes you can have issues. Any other development tool, this is another reason I would recommend using Easy EDA with JLCPCB, especially if you're just getting started out. All these components are placed perfectly, they're rotated right, so forth and so on. But let's walk through the capacitors here. So you can just click on each one of these elements and it will zoom in, and you can verify the placement and the rotation. Obviously, these are not polarized capacitors, so it doesn't matter the rotation. They just need to be placed properly. There's the first chip where rotation matters, and you can see we have a little purple dot, which is pin 1, and it matches up with the silkscreen dot denoting pin 1, and it matches the pin on the 3D representation. So you've got kind of verification in triplicate that this part is placed properly and it's rotated properly. These are the headers. The headers are placed properly. Not much to talk about there. LEDs, LED rotation matters, and I believe we've got that right. You can verify that with the, obviously, if you place an LED backwards, it's not going to work, but those are right. Resistor orientation doesn't matter there, but they're placed right. There's R5, R6, R7, the switch, U1. You can see our silkscreen dot matches up on the dot of the chip and matches up with the purple dot. So everything is aligned properly. There's not a silkscreen dot here, but you can see the dot on the regulator matches up with the dot on the 3D viewer, so we know that that chip is oriented properly. This one doesn't really have an orientation, but it's positioned properly, and obviously the USB is in here well. This is a full 3D viewer as well, so you can kind of zoom around and check things out and fly around. I love these 3D viewers. I've spent many minutes admiring my designs in 3D. My point is that you should, even if you used Easy EDA, step through every single component on the chip and just make sure, double check and verify. It cannot hurt. I've never had Easy EDA misplace anything, but it's just good to know. You might see something here that you didn't before. Even if you did the 3D view in Easy EDA, this is just very thorough, and it's a way of clicking through every single part. It's really cool. So now we're going to do next, and we're going to get into the nitty-gritty of pricing. So our total price is $46, and you're like, oh, that's not bad. The PCB price is $4. Like, the base PCB price is just so dirt cheap, it's not even funny. But the economic PCB price is much more expensive, and we can break this down a little bit. The setup fee, I think, is just pretty much unavoidable. Then we have the total fees for the components, so that's $12. And you can see why, you know, if we'd gone down to 2 boards versus 3 boards, it wouldn't have saved us all that much money. The extended component fee, however, that does get into some math. So we had 5 extended components, or 5 sets of extended components, so 3 times 5 is $15. And then we have assembly, hand soldering labor, so $3.50. Somebody actually has to physically solder some of those larger through-hole components on there. You could get rid of that by taking all the through-hole components off of there. The USB-C, I think, is handled by automated assembly because it's such a common part, but the pins that I put on there are not. So we could remove those pins from this order and I think save that $3.50. So let's actually go ahead and do that. I'll show you how to do that. And if we go back to our bill of materials, there we go. So let's not select that part. So it goes down to 0. We do next. It's going to give us a warning. It's going to say project has unselected parts. We're going to say do not place. Here are empty holes on the board. So when we get this, we'll have to solder in our own pins. But if you're like me, you've probably got tons of these pins and it's relatively easy to solder them in. And let's see what that does on the next page. It's come down a little bit. So remember it was $44 previously. We've saved $3.50. So we got rid of the hand soldering fee. You know, if you're comfortable with hand soldering those pins, I am, this will save you money. And I'm going to go ahead and do that. Now we have to select a product description. I like to go into the research, education, DIY, entertainment, and do development board, just for everything I do, even if it's not a development board. And now we're going to get the final price. And this is going to be some sticker shock. We're going to go ahead and do secure checkout. It's giving us this shipping estimate of $23.45. It gave us a coupon. That's nice. Let's do our secure checkout. I've already scrolled past the address because you don't need to see my address. The address is off screen. We can see the total here, and this is where it gets fun because, boom, we're having a big shipping estimate and customs duties and taxes. So it was $41, but in the end, our grand total is $103. That really, really hurts, right? You thought, oh, it's going to be $40 to get 5 versions of that. That's not all that bad. And it's a custom PCB, $8 each. It's a custom PCB I built. That's so cool. Well, now it's going to be $20 each. Ugh. There's not a lot of way around this. You can select the CPT shipping and it gets rid of all the customs duties, and I don't know how they send it. It takes a long time. Like, it takes a really long time. I think they put it on a boat. Like, I did this and it took 4 weeks before I even heard about it in the United States. And then every attempt I had to look it up, it just said it was like wrapped up in customs. And then it just came to my house like a couple weeks later. I had honestly given up on it. I would not recommend the CPT shipping because I think you're basically skipping out on the customs duties. I'm not sure how it's handled. Like, nobody actually reached me to charge me for customs duties. So I'm not sure if I did it right or if that's even a reliable way of getting things. It might have just been such a small package that somebody just moved it along, even though they were supposed to reach out to me and say, hey, you haven't paid the customs duties. You have to pay the customs duties to release this package. So I would recommend using the cheapest of the DDP options. So the DDP means that the customs duties and so forth are rolled into this. So I think just go with UPS Express Saver. So that'll get it to you a little bit cheaper. And then you can go ahead and continue. So then you can continue and order payment fee and go ahead and do cool pay. We have 2 valid coupons. Oh, can I do both of them? I can only do one of them. Darn it. Okay, so that saves me $9. That's very cool. So if you order stuff on here, sometimes they'll give you coupons. Go ahead and pay. And we're done. They've sent my part off to manufacturing, and I should get, within a week or so, my custom PCB in the mail. Awesome. We're done. All we have to do is wait until we get this part in the mail and then test it. I don't know, I might do a follow-up video on that. I definitely want to make sure that it works. If it doesn't work, I'm going to go in and I'm going to update the schematic and update the PCB. I'm pretty confident that this will work. It's such a simple, such a simple component. I'm very confident that it will work and do what it's supposed to do. There's not really a lot of moving parts here, but I could have gotten something wrong. If you see anything wrong, let me know in the comments, you know. I can certainly go in and update things or put a note in here as well. Thank you for coming along on this journey. I know 2 hours is a lot to ask people to want. I think this has been a relatively simple entree to getting your own PCB created. I haven't really gotten lost in a lot of the technical details. I take a very pragmatic approach to this sort of thing. You know, I leaned on ChatGPT a lot. I am not an expert in electronics. I am not an expert in PCB design. I am an expert in getting things done. Usually if I have a goal, I can achieve it. If I have a particular goal that I want to achieve with a circuit or a program and so forth, I can make it happen. And so this video series has been a representation of that, a very pragmatic approach to just getting it done. We set ourselves a goal and we created a board to do it. Is it the most perfect board? Did I do everything exactly the right way? No, I'm sure there are things that you could critique me on every step of the way. There are decision points that could have gone in a different direction. I think that's one of the things that people get held up on. They get kind of held up in analysis paralysis around doing these sorts of things. I know I have sat on board designs for a very, very long time, overanalyzing and checking and then sending them to review on a Reddit group and so forth. I think sometimes you got to just push that button and go and say, well, I might have just wasted $100, but I did my best, and even if I wasted $100, I'm going to learn something about this. I hope this was helpful. If you've got any comments, critiques, suggestions, please leave them in the comments. Totally would like to hear your feedback on this project, whether or not you think it's appropriate for a beginner, if you have any suggestions. Thanks for watching to the end. I hope you actually do make this project and submit it to JLCPCB and enjoy your USB breakout board.